This video will define a final structural measurement for the various molecular coordinates, and that is going to be called an out-of-plane angle. So an out-of-plane angle can be defined simply as an angle by which a vector is out of a plane. So seems like a fairly straightforward definition. So as we saw from the previous video, Z matrices are sufficient to define unique molecular coordinates. If you've got bond angles, bond lengths, and torsions, you can define a molecular structure. But sometimes it's more convenient to work in other terms. So for example, in formaldehyde here, which is H2CO, I've got carbon, 2 hydrogens, and an oxygen. And in its natural state, this is a planar molecule. That's the minimum energy structure is planar. So any 3 points define a plane, but 4 points do not necessarily need to be in a plane. So we can determine the extent to which a molecule is planar in a certain section by an out-of-plane angle. So we could define a plane, for example, by these 3 atoms, the 2 hydrogens and carbon, and then we could figure out how much the vector, the bond vector of the CO bond is out of the plane of the HCH plane. So that's one case here where it's particularly convenient to use out-of-plane angles, and that's our motivation for defining them in this video. Okay, so I have that case there, which is the simplest possible molecule where I have an out-of-plane angle. Okay, so mathematically we're going to have 4 points that are going to be points in 3-dimensional Cartesian space. So we're going to have these 3 bonds going on here. We're going to define the points I, J, K, and our central point will be L. So what we've got here is we're going to have L, J, K are going to define a plane. So for example, we could have HCH in this case. And then you see how much the CO bond vector falls out of that plane. So we could have another situation where I draw the plane here. And let's imagine I have some distorted geometry there. So I can define kind of a vector going through the plane. Then I have the plane of the 3 atoms there of my J, K, and L, atom I up there. Then I can define a normal vector to this plane, which is some normal vector to the plane, normal unit vector. And there will be some angle between that unit vector and this bond vector Li. And our out-of-plane angle of interest I'll define as gamma IJKL. So the thing we're going to be measuring first is actually this angle here, but you'll notice since this is a normal vector, it's perpendicular to the plane. It's 90 degrees. This is also 90 degrees, the sum of these two. So these 2 angles are going to be complements of each other. So this will actually be 90 minus phi. All right, so other details that we need in order to compute this for these 4 points. Okay, so we had, as I said, our central atom is L. So we have 3 unit vectors of interest, r hat Li, r hat Lk, and r hat Lj. We also need to make sure in this case that IL, JL, and KL are all bonds. Those things are all bonded. Okay. Then we can define mathematically what this unit vector is that is normal to plane JLK. So we're going to have r hat JL, unit vector JL, cross product of that with unit vector KL, divided by sine theta JLK. So that's another quantity I have in here is theta JLK. That just normalizes this cross product to make sure the cross product is also a unit vector. Okay, so that quantity is going to be this n hat JLK. as we've defined up here, normal vector perpendicular to the plane. Okay, so we're going to have the dot product n hat JLK dot r hat Li is equal to, and we know the dot product of two unit vectors is equal to the cosine of the angle between them. So it's equal to the cosine of, we know this is the complement of phi, so phi plus this equals 90. So this angle is 90 minus phi. And if you plot the function cosine of 90 minus phi, you'll notice that that function is also equal to sine phi. So we can use that as well to simplify this, because it's easier to write sine of phi than cosine of 90 minus phi. Okay, and then we can take the arc sine of that and get the final value that we need. Okay, so simplifying this into a final expression, we have that phi ijkl equals the arc sine of the quantity r hat lj cross r hat lk dotted, resulting vector dotted with r hat li, and that is divided by the sine of theta jlk. Okay, so this is our final expression for what this out of plane angle phi is going to be. Some restrictions on what the values of out of plane angles can be. As you might guess, normal vector angle relative to it, we can have a range of minus 90 degrees. Minus 90 is less than or equal to phi of ijkl is less than or equal to 90 degrees. So the most that it can be is in the plane, which it can be 0. It can be perpendicular to the plane, which is a positive 90, below the plane, which is a minus 90. This unit vector here, n, is defined by the right-hand rule of this cross product. So if I reverse the order of these two vectors here, or if equivalently if I switch j and k, I'm going to switch which way this unit vector points, and I'm going to switch the sign on my out-of-plane angle. So we can encapsulate that statement in the symmetry that phi ijkl equals minus, sorry, not phi, gamma. Have I been saying phi this whole time? I should be saying gamma. Okay, so gamma ijkl equals minus gamma ikjl, where I've kept the same out of plane angle, the same out of plane atom, the same central atom, but I'm switching the two other atoms that define the plane. So I'd be double counting there if I include both ijk and ikj. So that's another thing I'm going to keep an eye out for. Okay, so we can move over to the web browser now, see this program that I've got that does this inside of Jupyter. So this is the same as the torsion program from previous videos, and it has a few things added on now as well, as has been the theme throughout this chapter. So there's a new function for printing the out-of-plane angles. It's very similar to the function for torsions. A lot of the same math functions. A new function for calculating the out-of-plane angle. See the three unit vectors, cross product, dot product with the normal vector, out-of-plane angle from the arc sine. A lot of same determining functions. Again, several nested loops making sure that I is bonded to L, J is bonded to L, and K is bonded to L. And now our main block of our code has two new lines, getting the out-of-plane angles from the geometry and the bond tree, and then printing those values to screen. So the values that I have out here, if I execute this script for the out-of-planes.py for the geometry of formaldehyde, the molecule I had from Avogadro earlier, those are its XYZ coordinates. If I do that, printing out the initial geometry, the three bonds and their bond lengths in angstroms, the three bond angles. Notice that it didn't find any torsions because we didn't have any cases with three consecutive bonds. And then three out-of-plane angles, how far the oxygen is out of the HHC plane, how far hydrogen 1 is out of OHC, how far hydrogen 2 is out of the other OHC plane. In all of those cases, this molecule was very planar, so those are all 0. In other cases, you'll see values that are farther away from 0, and if it is perpendicular to the plane, then you'll get a value up to positive 90 or minus 90 degrees.